Okay, we're at 2 past, so let's go ahead and get started. Today's webinar is about manufacturing-ready design for additive manufacturing optimization, and really how we're going to do a design process automation for AM inside Synera. I'm really pleased to be joined today by two people I consider to be good friends, not only professional colleagues. Joining me is Rushik from Cognitive Design Systems and Thomas from Hexagon. Rushik, why don't you introduce yourself first? Looks like
thank you for having me. It's a pleasure to be on this panel with Thomas and Andrew, both of you. So I'm Rushik Matroja. I am one of the co-founder of Cognitive Design Systems and also a mechanical engineer by profession. I enjoy, the passion is design by all means, and that's what we are going to discuss today. Thank you for having, and thank you for joining.
Thanks, Rushik. Yeah. Thomas, why don't you go ahead?
Thanks for having me. Hello, everybody. I'm Thomas Raya. I'm responsible for the generative design business at Emendate. So for design optimization, automated design optimization, I think that's really fitting to this topic over here. And I'm glad that we have this combination of the three software packages really making a positive impact on the workflows. So I'm eager to see what we are presenting today and show to you.
Thanks, Thomas. And of course, my name is Andrew Setterelli. I'm one of the product managers here at Synera. I'm also our software partnership manager, and that's why I'm joined today by two of our great partners to talk a bit about how Synera and our partners work in the additive manufacturing space. Really today, in the engineering space, when we talk about mechanical engineers, design engineers, people that work to actually build physical parts, they're really entangled with a lot of different problems. Folks are trapped between their different silos. So you have your simulation engineers, your design for additive engineers, your manufacturing engineers, and they all are split into different teams, and they have to work somehow together, but also independently. Oftentimes, the work that happens between these different teams is very sequential. Design comes out, it goes to a simulation analyst, then it goes back to the designer, they make some updates back to the simulation engineer, then to the manufacturing engineer. It's all a very manual process that goes back and forth between different players here. Of course, as we start to think about what types of software tools are being used in DfAM, right, we have experts that are very specific in maybe a topology optimization solution, build prep solution, and the use of those tools doesn't really get democratized outside some individuals. And of course, to get into a new specialty like additive manufacturing, it takes a lot of knowledge and know-how to get there. And the people that do have that knowledge can become bottlenecks for the rest of the organization because it's really hard to get up to that skill level that these experts are at. And so at Synera, we think about how can this really be accelerated? And there's a few approaches people take to accelerate this design to a manufacturing process. You know, people start to hire new people to join their teams. So you hire a new additive manufacturing design engineer. Of course, you hire that person in-house. Well, it's very expensive to hire new people. I think we all know this challenge in today's market. It's difficult to scale. So you hire somebody maybe for a project, but you have to keep them on full time. Alternative to that, for scaling the amount of manual work that gets done, you could look to an engineering service provider or outsource to a best cost country. Of course, that's a bit cheaper than hiring somebody in-house. It allows you a bit more flexibility in scaling because you can scale up people as projects begin or wind them down as those projects end. Of course, it also introduces overhead for your existing engineers to oversee these folks and maintain that level of quality that you would expect from your engineers. Of course, if we look at the other side of things, not increasing the amount of manual work, but using automation to try to solve some of these problems. We have tools like TCL scripts, ADPL scripts, Visual Basic. These are all kind of environments built into a lot of engineering tools, but they're very specific to that individual tool. So it's a single purpose script that doesn't allow you to really connect between these different silos. Of course, today, very common Python. I think most of us that have come out of university relatively recently, we've learned Python or MATLAB, these sorts of tools. It's a great resource. It's very well known, as we said, but really it lacks integrations into engineering software tools. It lacks the ability to easily visualize the script that you've created if you're working with 3D geometry or simulation and these sorts of things. So there are options to really scale up the ability to address some of these problems in the design space. But this is really where we see Synera coming into play. So in a perfect world, engineers could automate any aspect of their development process. In this case, we're going to talk about a design for additive manufacturing development process. But engineers can create those processes. They can then reuse them. So you're not starting from scratch. You can share them with your colleagues. So if you're an expert engineer, you can create a workflow, a process, and then share that down with a new hire and help them understand how your company goes about designing and engineering products. And of course, as we automate things, it enables us to ensure that there's quality throughout this process that's standardized, so that one engineer isn't producing different outcomes from another engineer in our development processes. And so at Synera, we've created this visual programming language specifically tailored for engineers. And that's the important thing here. We're predominantly mechanical engineers at this company. We've worked in the space. We have customers that are dedicated in this space. And we really crafted this product for this type of person. So it allows you to automate your tasks that you've constructed in this process canvas that you see here. And we'll give you a demo of that in a few minutes. That allows you to visually construct your workflows rather than having to type out a script. Really, if any of you have ever tried to share a script between colleagues, it's a pretty difficult task. Good luck trying to understand what your colleague has done 12 months ago or what you've done maybe 3 months ago. It becomes very intransparent as you try to share that knowledge. And that's really what we're trying to change here with this visual way of constructing workflows in Synera. And of course, as we talk about those workflows, the important aspect here is that we're not constructing these entirely on our own. We're partnering with so many other companies like Cognitive Design Systems, companies like Hexagon, Autodesk, Siemens, EOS, PTC, and the list goes on. So today we have 20 plus software partners, 47 add-ins in our marketplace, and all of these add-ins are accessible by our users to help them construct the workflows that they want. And so today we're going to talk a bit about some of those different technologies that we have inside Synera from our partners here, and then take a look at a workflow that we put together to go through really design for additive manufacturing for, I would say, a relatively well-known component here. So at this point, I'll turn it over to Thomas. Tell us a bit about what is Hexagon Emendate.
Yeah, thank you. So first of all, let's put a statement here. I think it fits well to the scheme of automation, what you said as well. Generative design is not going to take your job, but it will make you better at it. The idea is, as we have just learned, we have a lot of challenges like getting the right people doing the job and having the time for it, and the complexity of the challenges that we have to work on as an engineer. And we should use software. We should use whatever we can get as a tool to make our job better. But I believe it will not replace us, because there's still the engineer doing the final decisions and telling the software what to do. But hey, let's use it to get better at our job. Maybe get out of office earlier the day, but having the job done. So first of all, why generative design at all? Optimization, additive manufacturing. I think you know that additive manufacturing can print everything you like. Well, that's not correct. We know we cannot print everything. Additive manufacturing is, as every manufacturing method has its specificities, and you can get issues if you have the wrong design. So you need to make sure that you create a design that is manufacturable, and that's what we are talking about today here, how we can get that with the help by Hexagon Emendate and cognitive design systems. So Hexagon Emendate basically is a kind of an optimization tool. So generative design and design optimization is often mixed up and it's close together. But like a standard topology optimization has some issues in the design generation, as you see on the right side. It can have unclear results, problems with resolution where it's not sufficient. You cannot really show the details of a part of a geometry. Like if we have a look at additive manufacturing, even lattice structures, well, it's very hard to really optimize them. And basically, and I think we will see that by Rushik more or less later on, I believe that for topology optimization, lattice structure is more than questionable. It's something not perfectly made for a perfect structural point of view, what would be topology optimization, but it's for manufacturing and it has a lot of different other positive sides. You cannot create it with topology optimization. That is where you get some things like discontinuous connections or issues where you're not clear what a design should be. And this is where we say that we need an optimization approach. It's not just topology optimization, but which is generative design. So generate a design. This is my interpretation of the word generative design. We generate a design and not just have a mathematical calculation solved. So for me, generative design is where you get something that is manufacturable, more or less. You get different designs which are all feasible. So in our case, Hexagon Emendate is always optimizing for an equal stress distribution. At the core, for sure, you can put a lot of different goals and objectives on top and manufacturing constraints, but all of the results are meeting a certain stress limitation. But they can look very different. Some could be more lightweight, some could be less lightweight, some could just look ugly. Yeah, honestly, most really ugly looking designs typically are just wrong. But some designs might look better and some look not that good. Or some could be easy to clean or not. And in the end, you have to manufacture it. So we say that you should run an optimization and the topology optimization in the background, but always try to get the best result for all of your requirements. And maybe these still do not fulfill all of the requirements because you might have some things where you would like to go for some even more complex structures, like lattice structures or something like that. That's what we see later on with CDS. But generative design is taking care to get these designs which can be usable. And if you want to have multiple designs, this does not work if you make all of them by hand or with bad performance. So we are taking care that you are as fast as possible, like using GPU computing, which is significantly faster, or overall saying reduce the time, because automation, that's a perfect match. We are trying to do that in the small area of our own code, of our own optimization, trying to get rid of as many steps as possible, just throw in the geometry and the boundary conditions and everything around smoothing and geometry recreations done by the software. But especially inside Synera, it's really reducing the time because you can always set up one workflow with all of the complexity and back and down to the additive manufacturing specificities, and then just change the very early design question, maybe for a slightly different product. And all of that is running through and you get back with a significant time reduction, the next feasible design. Here, just two samples of what could come out. Here, like a diode arm, it's for chip manufacturing. At the top, there's a laser diode mounted, and it's possible to reduce the weight by 40% while increasing the stiffness, the linear static stiffness, as well the ion frequencies, and still keep it easy to clean. You might say easy to clean, might be questionable, especially at the top, but that's what we talk about when we talk about the design funnel 2 slides before, the generative design. You run multiple optimizations with different parameters and then interpret what is easy enough to clean while having good enough performance. And here, research instruments, our customer said, okay, this is easy enough to clean. We can just do that. That's fine. But we have very good performance. And other designs might be simpler, but not having that performance. Another one, very small and easy, it's a spare part for a train. And in this case, it's we could not imagine that additive manufacturing of this is really a good idea, but because it's small and quite heavy. But yes, we can reduce the weight. Adapted to AM was taking care of the overhang angles and the minimum and maximum strut thicknesses. So good to manufacture and still making it happen fast, because running this design creation is done in 2-3 hours completely. You got the job done and you have a new design as a spare part. So saying generative design is not taking your job, but it will make you better at it. It will make you faster. Nevertheless, as I said 2 or 3 times, these designs are good designs, and we take care to make them as close as possible to additive manufacturing. But still, if we're going for some kind of topology optimization as an FEM-based process, we have issues with very small geometries of additive manufacturing. And sometimes, even though we try to take care, you could get a better design that's more easy to manufacturing. And this is what Rushik will tell you about.
Thank you, Thomas. Yeah, and thank you very much for your presentation. I like the tagline. It makes us better, and that's exactly what we are trying to achieve here with our tools, with cognitive design systems. The whole goal is how to create workflows which are manufacturing-driven designs. So keeping always the manufacturing at a focal point to make sure that we have designs which are always manufacturable. When I say manufacturable, it's not only that it should be fabricable, but we have to also understand what are the costs related with it. We have to also understand if it makes business case out of it, but also what might be the carbon footprint of it. So all this other criteria, which also comes as a key to decision making of whether we will go for a specific process or another process, is very important. So a little bit introduction to the cognitive design systems. We are a company based out of south of France in Toulouse. Little bit less known than Hexagon, but with a great ambitions also. We are a team of 18, and our background is from Asia, from Japan, where we work with a lot of automotive industry, automotive companies. And now in Europe, we are also working with a lot of aerospace companies, as we can see here. The next slide is to understand the vision of the company is what I mentioned earlier. We want to make sure that the manufacturing insights are taken care while designing a component, because that's a key to a successful design. And in order to do that, we are able to get, first of all, analyze the part for its feasibility, for its manufacturability, for its cost, and then we take the right steps towards in the design modification to make a part manufacturable. So when we have a great looking part from Hexagon, from topology optimization, we also want to understand that, okay, what would be the cost to manufacture this? How can I change the parameters of topology optimization to achieve a lesser cost? How can I change other parameters to achieve a better manufacturability, etc., are something that we need to take care of. In order to do that, we developed 3 core technologies. So first of all is the manufacturing and feasibility analysis tool for additive manufacturing. It's also in our standalone tool called Cognitive Additive, where we go through risk analysis, costing, carbon footprint analysis, tool, and it helps us to also bring some of the customers who are new to additive manufacturing to adopt the technology in the right way to create components for that specific technology if it makes sense business wise. Second core technology is our hybrid geometry engine, which we created from scratch. It's called cognitive design, where we use implicit modeling and we automate design workflows in order to understand that, okay, from getting the insights from the simulation data, from the manufacturing data, and how can I rapidly change the design to make parts manufacturable and better in general. And all this brings us to the manufacturing-driven design, where we actually create repeatable workflows which are easy to use, which are fully automated and configurable. And some of these workflows are in Synera, and we can use it in tandem with other plugins such as the Hexagon today, and that we will show in the demo. Sorry. So the cognitive additive, which is the AM analysis tool, it works for powder bed fusion, FFF, MJF, binder jetting technologies. It's something that is that works on your PC, so we don't send any data outwards. So you can be very safe with that. We do feasibility cost analysis and the manufacturing risk analysis, and we generate a report that we will see today that helps to quickly assess how to manufacture this part, at what cost, and what are the risks related with the manufacturing. On the cognitive design side, which is our geometry engine tool, where we have solutions such as simulation-driven design, where we can take the simulation data and apply it on varying thicknesses of the part itself, thicknesses of the TPMS, lattice structures. We can create variable ribbings, shelling. We can automate the Boolean operations. This kind of operations can be completely automated. And as you can see, that where the stress is high, we can actually have a thicker zone. Where the stress is low, we can have a thinner zone. So we can better manage the material distribution doing this. We have also another tool, which is a process which is sometimes quite time-consuming. Results coming out of topology optimization. On Hexagon, it's a very special case. It's they are bringing up some really good parts. So we don't have a lot of work to do, but sometimes it's required to do some modifications. And this modifications requires to bring it back to the CAD environment, doing manual operations. Instead of doing that, we have automated the topology optimization reconstruction process. So if there is any kind of small issues with your part, we can completely automate the morphing of the design to make it more manufacturable, put the right thicknesses along the part, apply right overhangs along the part, such like this. And this is also something which is available in Synera. And this brings us to the demo, and I give the floor to Andrew to show us the demo. Thank you.
Thanks, Rishik. Thanks, Thomas, for giving everyone a bit of an overview as to what you guys are doing at your companies and how it's all happening inside Synera. Let me just take a moment here, and I will get Synera up on the screen here. So what you see here now is Synera. So we have the canvas on the left-hand side, very familiar environment to those of you that have maybe in the past used Grasshopper or Dynamo or tools like this. And on the right-hand side, we have the viewport, very familiar for everyone that's used a CAD system, a simulation tool in the past. And we've combined these together to allow you to start to construct different workflows. Now, those workflows can be very basic. We're going to step through this topology optimization one, but maybe just very quickly here, we could have something where we just construct a sphere, right? A very basic workflow. And all I'm doing is dragging and dropping different nodes together here. And we can start to see now, if I zoom in, as I change my radius here with this slider, my sphere changes shape. Now, obviously, workflows for engineers tend to be a lot more complex than simply constructing spheres. And so, again, that's why it's nice with Synera. Everything that Thomas and Rushik have shared with us today about their different products are accessible and entirely licensed inside Synera and accessible to all of our users through the marketplace. And that marketplace is where we bring those third-party technologies together. But maybe to start things off here with this workflow for additive manufacturing, we're going to step through. Oh, give me just 1 second. It looks like I've got to recompute here. We're going to step through the process that some of you may be familiar with the was a challenge put out by the Jet Propulsion Lab in the US with a simple example of a type of part that they would like to see optimized. And so what we've done, and I'll zoom out just a little bit here, is constructed a few different workflows, and we'll step through the process to try different variations of part design here. So you can see an example here of the type of geometry that we're getting out of Hexagon Emendate from Thomas. And of course, then, well, if we start to look at different design variations, we're going to want to compare those against one another. And so we took some values out of cognitive additive for the different designs that we came up with for the different expected prices per part for manufacturing, and also the total build time that we may be expecting here. Now, obviously, depending on your use case in additive manufacturing, you may have different constraints. For, let's say, an aerospace application like this bracket, you may not care so much about cost and build time. You're much more concerned about the end weight of the part, as that greatly impacts the cost it takes for that to go to space. We're talking about an automotive component. Well, the build time and cost are going to be much more applicable here, driving constraints for you, because obviously if you're manufacturing 100,000 components by additive manufacturing, you need to drive the cost down. And so what do we have for a workflow? Well, a workflow here typically starts with importing different geometry. In this case, we're importing a step file. From that importing of geometry, we'll go through and generate a mesh of this part. And that mesh is going to be used then to run an initial simulation, an initial validation of this geometry to understand what its performance is. Now, the great thing about Synera is we have our own internal FEA solver, but if you're using MSC Nastran from Hexagon or Altair OptiStruct or ANSYS Mechanical or Abacus, you're able to connect to all of those tools and use that to perform your validation of your initial part, your validation of your end part here. So once we've done that initial validation, we'll go through and we've set up some different loads and boundary conditions on the different areas of our part based on the coloring of those surfaces that when we imported them. Now here we've kind of hidden away the workflow that's used to define the boundary conditions, but the nice thing here is we can start to layer in that complexity in our canvas here. So if we wanted to, we could go ahead and open up one of these subnodes and see the bigger workflow. But here we're going to stay at the high level so we can step through the rest of the process, which is after we define boundary conditions, we're going to go through and actually set up our optimization process. And for that, we need some material. We need to know what our design space is, what our loads are. And in the end, we can get out, let's say, a fairly nice geometry, I would say, Thomas, from Emendate directly. Now, we showed in one of our other webinars how you could actually use Synera to step through kind of varying some of the input parameters for the component. We have this complexity input here for the topology optimization with Hexagon. And so we could start to do variations on that and understand how that input variable then impacts our outcomes. And again, start feeding that into some of these tools like cognitive additive to understand pricing, manufacturing time, and other inputs that are important for evaluating components for design for additive. But we're going to take this part here and we're going to actually improve on it. Sorry, Thomas, because I think Rushik has some great technology here with cognitive design, and we can start to play around with some different variations of this geometry. And so let me just go ahead and hide that one for a second. And let's take a look here. So the first node that we ended up using was this variable lattice infill component. And so this allows us to use simulation data, maybe some of the simulation data in our initial design and the validation of the optimized design, to then start to augment the geometry that we have here. And so actually we end up with some really nice infill geometry on this component. Rushik, maybe what types of lattice structures are possible with this lattice infill? It looks like you're still on mute, Rushik.
Yeah, there are plenty of different lattice structures possible. You can create lattice structures, PPMS structures. If you go in the down the menu, you will have that. Okay, you have some basic lattice structures like a cubic, FCC, and star, but you have also some other more complex lattice structures that you can use. Same way, these lattice structures, you can change their cell sizes, thicknesses pretty easily, and you can actually thicken the lattice structures based on the stress results that you have obtained from the FE analysis. So you just have to input the FE analysis results. You say that, okay, based on the displacement or the von Mises stress, I want to modify the lattice structures, and then it will automatically modify those structures locally, so you don't have to do it manually.
Great.
Same for the TPMS, yeah.
Yep. So we have, in this case, we stepped through 4 different possible scenarios here. So first we use the variable lattice infill, again, coming up with that nice star-shaped lattice as the infill structure here. Then we went with a typical gyroid structure. And here you can see that geometry there. So a nice triply periodic minimal surface that we've applied inside this using, as Rushik said, the implicit design capabilities of cognitive design. We then took a look at the kind of just basic topology optimization reconstruction. For any of you that have gone through this process before, you know that it's quite time consuming, selecting all those surfaces to preserve and constructing that. And here it's simplified into a really nice basic node that can really easily be used and applied in different applications. And then we have the variable offset thickness. And I guess this is, again, using simulation results to drive the thickness of our geometry. Obviously, for some parts, having a hollow component can be advantageous to reduce weight. Now, all of these are really nice designs, but of course, we need to take a look at what is the actual manufacturing outcomes we have here. And so that's where, let's say we analyze a component like this. We can actually do a manufacturing analysis with cognitive additive and come out with different attributes about the total printing time, the labor required. And of course, all of this is defined by the user. So you have full control over how this costing happens. If I just quickly jump over, I can take a look here. And so you see that you have the ability in this process to fully define your cost profiles. So you're going to define your machine, what material type you're using, your different process parameters, and some basic attributes about the cost to run the machine, labor costs, things like that. And all of that's going to help you then go ahead and generate this evaluation of different parts. And of course, we have all of the printability attributes here as well. And so again, we can sum up all of this data quite easily inside Synera, and then come up with a quick evaluation then of how different outcomes have different prices, build times, these sorts of attributes. And let's say
I would
we
like
want
to add one small thing, Andrew. That okay, when we are doing this this analysis for pricing and feasibility, on the behind of the scene, we also do the orientation, finding the right orientation to print, doing the right nesting to print, and based on that, we also estimate what are the support structures, what will be the volume of the support structures, and based on that, the pricing comes out. So it's not a volume-based pricing. It's much more in-depth analysis of detailed pricing based on the orientation. Also in-depth analysis on the feasibility that okay, if we are printing it in one direction, like the Z positive, like this one, as we can see, the pricing will be different than if we have another orientation where there are lots of support structures. So this is also very important piece of information that needs to be how can I say, automate to be able to take the right design decisions.
Great, thanks, Rishik. And so maybe the final thing to hit on here is all of this has been constructed in a visual workflow that you can see here. And it starts at the beginning simply with a step file. Now, what often happens in a design process of any kind, your design changes, and then all of these downstream steps that we've talked about here, when they're done manually, you have to go in and manually redo them all the time. And then the nice thing here is, if we were to say, change out this step file for one that's slightly different, this entire process is going to replay itself. So once you've created and captured this workflow once, you can replay it and reuse it multiple times afterwards, which is really saving a lot of time in this design for additive manufacturing process, because as we all know, things rapidly change, concepts change, your packaging requirements may change. And so now we can help you respond a bit faster to those demands by combining all of these tools together in a very simple automated process here. So maybe let's take a step back and jump back into the PowerPoint quickly. And so at this stage, we do want to open it up to questions, if there are questions. And I did see one that came through on the Q&A. So Peter asked, does the cost estimation also respect the stackability of the parts?
Great question, Peter. Yes, indeed. Actually, we do the nesting of the components. So you can import multiple components, or you can select a quantity of the parts that you want to produce, and based on that, we will based on your machine that you have selected, we will try to stack the maximum number of parts on the plate, and the cost will be derived from that. So it's not a per part cost. It's a
Great. Thanks, Rishik. And maybe to Thomas, what types of AM manufacturability constraints does Emendate have?
Yeah, I think I had it in a side sentence, but yeah, so we can take care of support structure reduction, so taking care of the overhang angles. We can have minimum, maximum thickness constraints. Not all of them directly accessible in Synera yet, but you can make them accessible if you want. And we're improving the UI based on, so the Synera UI, the accessibility based on the solver. Yeah, step by step, continuously. So furthermore, we take care that you don't have too sharp changes of thicknesses somewhere. So in fact, most of our designs are directly very well printable. The optimization was invented to create manufacturable designs, and just take care that it works. Looks a little bit like magic, but it is a little bit.
I always like a bit of magic in my engineering.
Yeah, sure.
Maybe a good one for Rishik. Implicit design or implicit modeling, it always maybe conjures up some different ideas or concepts in folks' mind. What can cognitive design actually do? We saw some topology post-processing here, but can you do heat exchangers? What else is possible?
Yeah, I mean, definitely, yeah. So the implicit modeling allows us to unblock some of the challenges that we have with the traditional CAD, where there will be some Boolean operations or some kind of filleting operations will not be able to do because of the complexity of the geometry. We don't have that issue in implicit modeling side. So we can actually go and create a lot of complex structures based on mathematics. So we can create complex structures for heat exchangers. We can also use implicit modeling to change the, how can I say it, the manufacturability of the part by reducing the zones where we have a higher thermal concentration, for example, while printing the part. Or we can also modify the geometry to make it manufacturable with conventional processes such as molding. So that's also something which is inside Synera, but not topic of today. We can actually convert any geometry into a moldable geometry using implicit modeling.
All right, I see another question here from Pedro. He asks, before topology optimization step, can Synera act on design features and optimize them based on custom defined cost functions? So that's a good question. So Synera is able to read in CAD geometry from any major CAD tool that you can think of. We also have the ability to interact with actually the parameters that you've already defined inside your CAD tool for your geometry. And so we could actually do maybe a more traditional parametric optimization where we're playing with some of those different design variables from CAD. And of course, as you saw here today, cognitive additive has costing functions for AM. We have costing functions for casting. We're working with other partners to integrate costing tools themselves inside Synera to bring these insights into the hands of the engineer, the designer that is trying to construct these workflows. So if you have a specific costing tool that you're interested in having inside Synera, definitely reach out to us to learn more. And I see another one, which is actually a great segue into our last slide here, which is, how long does it take to learn Synera? And so, or not to learn Synera, but to learn the software and all the tools that go along with it, which is a great question. So I think that really depends on your use case. We see people picking the software up quite quickly if you are experienced with programming. If you've used tools like Grasshopper before, then it's very easy to step into Synera and start using all of these different capabilities. Of course, we have a full learning content system as well that you can take advantage of to start to onboard into the software. But I would say the best way to learn the software is actually scan the QR code on the right here to sign up to get a customized demo from Thomas, Rushik, and myself on some different topics that you may be interested in, so we can really tailor the experience towards you and help understand what you want to do with Synera. And of course, if you're an existing customer, then please head over to the Synera Marketplace using the QR code on the left-hand side and download these great add-ins that we've just seen here today. So I know Thomas and Rushik and their teams are working hard and constantly to release new versions and updates on the marketplace. I think Thomas's team just released some new casting constraints, if I'm not mistaken, for Emendate. So exciting stuff available to customers today. I think that's all we have time here today for this webinar. I want to thank everyone for attending, and especially Rushik and Thomas for joining in today as part of this session.